So in reality, there are actually a number of other factors which affect the closed loop control system of an aircraft. Most notably, any atmospheric disturbances, for example, if we're flying through turbulence, and also our feedback loop, which relies on the accuracy of our sensors. So here you can see is a sketch or a schematic of a closed loop system for an aircraft. We'll start over here with the input or the command signal. That's given the notation little r if we're considering vectors, right? And this is input to what's called a comparator. Now basically this just compares two signals and then outputs another signal based on the comparison of those two signals. So this is where our feedback signal is going to be fed into, and it's going to be compared to the original input signal. So from there, an actuating signal, given the notation E, is sent out to a controller. In our case, this is going to be something like an actuator on one of the control surfaces, for example, and that then sends out a control signal which basically initiates a process. In our case, this will be the aircraft responding to that control input made by the controller, right? So whatever happens here, the aircraft responds to it, and then the new condition where the aircraft ends up is going to be our output, given the symbol Y. But while all of this is taking place, obviously other external effects are also impacting on our aircraft. So this is what we're going to generically describe as atmospheric disturbances. We have something called a gust vector G, which impacts on our process in addition to the impacts made by the controller itself. So that gives us our output. The only other thing that's connected to that is this leg here, which tells us where our control surfaces now are in relation to the 0 position, let's say. So if we've made a control input that's, for example, deflected one of our control surfaces to its maximum, then of course that needs to be fed back to over here, because now of course we don't have any more deflection in that particular direction, and then so that's not necessarily affecting the aircraft response to that control input. We just need to know physically where the control surface is located to work out whether we have more or less available to us, right? So this then formulates our feedback loop to our control system, following this blue line down in here. We have a measurement of some parameters. Now again, here, this is quite an important piece of the jigsaw here, because the precision or the accuracy of our measurements is obviously going to impact how effective our control loop is. So it's important that we factor in here any uncertainties based on our measurements that are taking place via our sensors. The information or the data from those sensors is then fed back into our flight control computer, which calculates the gain that needs to be applied to the actuating signal. Again, if this is adjusted such that we have negative feedback, the gain applied here isn't going to overcorrect for the initial input. All of those calculations take place. A feedback signal, given the notation Z, is fed back into the comparator, which then makes another actuating signal. And this process repeats until the desired flight condition is achieved. Now, there is a few laws which describe what's going on here, which I've tried to describe down in this corner here. So first of all, looking at the actuating signal E, that's just the difference between the original input signal and our feedback signal, which adjusts the controller on the fly to ultimately find the output that's desired. The controller signal, C, is some function of the actuating signal. So the actuating signal tells the control surface, for example, to do something, to deflect by a certain amount in a certain direction, and that obviously informs the control signal, which is basically the aircraft's response to that control input. So next we have the aircraft state vector X, which I've just added to this leg here. So that tells us the current condition of our aircraft, how the aircraft has responded to the control signal, and obviously that is a function of how the aircraft responded to that control signal plus any external atmospheric disturbance effects as well. So then all of that gets fed out to the output, which we give notation y, and of course that is some function of where or how the aircraft has responded to the process, but also contains information regarding where the controls are positioned at that moment in time as well. So a function of the vector x and also a function of the vector c directly. And then finally, we follow the feedback loop all the way around so that our feedback signal vector z is just some function of the output plus the measurement error that was made here. So this is the exact output. This is the output as measured by the sensors that we have, which have noise or error n. That gets fed back into the comparator via the feedback signal z.